1, 2, 3, 1, 2, 3. Hi everyone. As usual, I'd appreciate if you could let me know if the stream works and if you can see me. Just let me know through the chat if everything works, if you see me and we should be good to go. And of course, let me know in the chat, how did you learn about the stream? And where are you from? I always like to know, from where do we have people on the stream? That's always great. Okay, today we are going to talk about GLM OCR, which is a new, literally released a few days ago, OCR model that can do a lot of things. And while doing so many things, it's also incredibly tiny. The GLM OCR has like less than 1 billion parameters. And if you know anything about OCR models, released recently, you know that they are usually quite big and quite slow, and GLM OCR is actually the opposite. It's pretty small, pretty tiny, but at the same time really accurate. So here's the paper for GLM OCR, and maybe not a paper, maybe let's call it a technical report. And the important thing is here's the chart comparing GLM OCR against other top OCR models out there. And what you can see pretty much right away is that we have big names over here. We have Gemini, we have Qwen, we have OpenAI. So big labs scoring on this OmniDocBench benchmark, and the GLM OCR is actually beating all of them. And yeah, today we are going to put that benchmark to the test, but we are also going to test the model on different real life data sets, and we are going to build some cool demos along the way. So I hope that you will like the stream. Yeah, like I said, let me know in the chat if the sound works and where are you from. If you have any questions, of course, let me know as well. I will try to answer the question. I am, of course, not a researcher or anything like this, so I will not even attempt to have a deep dive into the architecture. But the important thing here is that we have like a two-stage model. The first stage is vision encoder, and that's CogViT with 400 million parameters, so fairly small. And another one is LLM decoder, 500 million parameters. So that gives us this less than 1 billion size, and that makes the model super fast. They use distillation from larger models to kind of like condense the knowledge from the larger model into this way smaller one. They also do like clever tricks like multi-token prediction. So you know that most LLMs, VLMs do like a one token per like a pass through the model prediction. They are doing like multi-token predictions. So like I said, I am not a researcher, but they gave us a little bit of information in the paper on how it works. Cool thing is that the model comes with the ability to read LaTeX or LaTeX and tables out of the box. I found this space. I will probably create my own one, but I didn't really have time. But I think we can maybe test that claim. So let's pick one of the tables from this paper. Something more complex. Let's go for something like this, yeah. And let's try to read it. I will show you how to run the code in just a second, but might be pretty cool to just test it out. So I'll just screenshot it. I will just drag and drop it into the space, and we will just run OCR. Oh, finally, we have some action in the chat. Thank you very much. We have a few people in the chat. Cool. We have the first one and the second one person right away. Takes a little bit of time to run that single table, but maybe it's worth it. We'll see how it goes. GLM OCR means space. I have I'm not sure, but we'll run it in the collab in just a second. So I will tell you guys how much memory do you need to have to actually run it locally. We'll see how it goes. Hi, everything is fine. Hi, Fi from Poland. Hi, Radek. Nice to have you here. And yeah, the table got extracted. Took us, I don't know, maybe 20, maybe 30 seconds, and I believe used this kind of notation similar to or maybe even HTML, probably HTML. And we extracted this. Okay, let's have a quick comparison side by side. So what do we have? Pipeline tools. This looks fairly well. The first line. Yeah, looks accurate. Of course, I didn't tested everything. Obviously, we'll probably need to have like a table extraction benchmark or something like this. But on the first glance, it looks pretty well. What else we can do is let's test the formula extraction. I don't think they have any formulas in this paper. There are some examples as well. We'll take a look at them. Attention is all you need. Yeah, attention is all you need. Let's take a look. There should be some formulas in that paper. Yeah, there's a formula for attention. So let's say we will just remove this image. I'll just screenshot this one. Just drag and drop it here. Say formula. Cool. I'm using the free version because I'm not logged in that browser, but sure. Let's switch to this. Let me just take the screen in here. We'll drag and drop it here and ask for the formula. It's take a lot of time. Yeah, it takes a lot of time, but I believe it takes a lot of time depending on the size of the image and the complexity of what you would like to extract. Because, for example, that table that we just extracted, it took quite a lot of time to run it. That's true. But it was also a lot of information to extract. So there's that. For example, for this one, when we only had this formula and the image itself was quite small, the extraction was quite fast, and at least on this image, the LaTeX extraction was actually accurate. So I believe, it needs to generate all of those tokens. So yeah, it's probably because of that. Okay, cool. We will be able to test it maybe right now. So I'm in Colab. It is what size of the Colab is this? Okay, so it's NVIDIA L4 with 22 gigabytes of RAM. And now I will show you how to run the model. The notebook that I'm, of course, using is in our RoboFlow notebooks repository. So I'm pasting the link in the chat right now, and I will also maybe send you a link to the actual notebook that I'm running right now. So yeah, so I just pasted 2 links in the chat, and I made a notebook so that it should allow you to run the model on Mac, on CPU, and on different versions of NVIDIA GPUs. We'll see how it goes. To save us some time, I pre-installed transformers in RoboFlow so that we wouldn't need to wait for this. And here I am pretty much done loading the model and loading that model into the memory. So that should give us a little bit more information into how much will it actually occupy on your VRAM. So that's it. At least for now, before the inference, it takes around 2.5 gigabytes of VRAM locally. And yeah, I have some utilities here. One to run the OCR and one to load the images from the data sets that I will use and pretty much to display those. So let's just execute this cell. And yeah, let's start with Captchas. Yeah, so with all of those questions like are you a robot or something like this, I decided it's probably the best idea to have the initial test. I'm using one of the data sets from RoboFlow Universe. We have this kind of like a small subset of Captchas that were, I believe, so generated with like some PHP library. So we can see that they have like a different level of complex, like how hard it is to read them. But yeah, definitely a hard test for OCR model. And I'm just using like a very generic prompt text recognition. So as for the speed, we can see that was fairly fast. Yeah. So we ran 9 different images from the data set and took us less than 2 seconds. But yeah, what are the interesting things we can see? Those easier captchas, I think, went fairly well. Here the model thought that those are 2 Qs. I believe those are 2 zeros. And here it's interesting because the prompt was so vague that it also picked up the Yandex text, not only the Captcha. So so let's do maybe something like this. Will it make it ignore the rest of that? Yeah. So what I liked about the model, it's that, so maybe I was like, what I like about the model is that you can fairly easily give instruction to the model. And in most cases, not all of them, because I have a few examples that I will show you in just a second, where it kind of like did not follow those instructions, like to the extent that I would like it to. But very often, all you need is just a little bit of like a more precise prompt, and it will get what you want. Yeah. So I think this Yandex Captcha is one of the like best examples to showcase that. Is that by default, if you gave it like a read text, it extracted all the information that were there. But the moment you said, hey, I am only interested in the code, it ignored that Yandex text and gave you the code. Yeah. So I think that's a pretty good representation. Now the next one is being able to extract those LaTeX formulas. So once again, we have a data set in RoboFlow where there are like thousands of different formulas with ground truths. And now we'll see if we'll be able to just recognize them with this like a fairly generic prompt. And once again, it's going pretty fast, probably depending on the complexity of the actual formula. Might be slower or faster, but it's going pretty fast, I'd say. So there's that. Would be cool if we could somehow validate that. So this is load the images, input, generated IDs, run OCR. Okay, prediction. So let's try to make it print. Prediction. Run this particular test once again. Weak LaTeX. Okay, let's try this. Yeah. So generated the, where are we? It generated those outputs. Now I think it would be pretty cool if we could just render that somehow. Okay, so we have something like this. And does it match? Okay, so we have this example, yeah, x prim k plus k squared m squared a squared. Yeah, I think it is pretty much exactly the same output. So, you know, it wasn't like a very deep test of LaTeX capabilities, but we ran two different equations, and we got exactly the same result as we should. So looks like it is capable. And those images here, they are, you know, fairly hard to read, to be honest with you. For example, this one, it's or here, yeah, it is not a very easy to read text. And even on those fairly complex examples, it's doing pretty well. Let me just paste another one. This one was a lot harder, I think. But I'm not like 100% sure, but quickly glancing at the result, it's pretty accurate. I mean, for sure, we could do something like this with like Gemini, yeah. But Gemini, we need to pay quite a lot of money to do it over the API, and it's not necessarily very fast as well. So this looks really impressive. The next one that I wanted to test is a data set of receipts from I believe like in Indonesia. I'm not sure, but if you take a look over here, we have part of the receipt that is blurred. Like this is probably the name of the restaurant that or shop where we got that, and we have the rest of that receipt is readable. And the question that I asked to the model is like, what is the total price of on the receipt? Yeah, and when we run it, and those I would say are definitely a lot more complex examples. It's still doing that in like 1 image per second speed, and yeah, the memory allocation does not move. It is like 2.3 gigabytes. Oh, now it moved. Now it moved. So to run this, it was 5 gigabytes of VRAM. And okay, let's take maybe like a deeper look. So for example, here the total was 197,450. So that's okay. Here it's 88,000. Here is 40,000. So yeah. So let's ask about something different. Like what is the maybe like read. So like read the list of products. I'm not sure if that's like a very accurate prompt, but we'll see how it goes. Okay, we are definitely extracting something. So this is like a list of product plus the amount of that product plus probably like a per item price, I think. Indonesia here. Thank you for finding Indonesian receipts. You can find them on RobFlow as well. So it will be kind of, I think, hard to read the actual values from those receipts if they have like a lot of items. But for example, this one is pretty easy. It's like a XXL crispy chicken, 1 item, 40,000. Yeah. Soft. There are probably some typos here, I believe. Soft steam. Okay. Yeah, but I think it's doing pretty well for the size of that image and for the like amount of items. It would be a lot easier if we could like see the image in a real size, but we can certainly ask about different things in the image and and extract it this way. And another interesting way how we could approach that is to try to extract it in a organized way. Oh, hi, Jeremy. Nice to meet you. I mean, we met each other, I believe, online, but nice to see you on the stream. North Carolina. Okay. It's awesome to see people from different parts of the world on the stream. Thank you very much for joining. Okay, so maybe we could ask it to extract it in a JSON format, yeah? So let's try to ask about the heck. Okay, guys, I have small technical issue. Give me a second. I'll try to solve it. Literally, my keyboard just died. So I'm not sure if okay. So we'll use a different setup right now because, like I said, my keyboard just died and it will probably stop me from doing the stream. So I hope it will work right now. Hope you guys still hear me. You probably won't see me right now, but I switched the camera. I plugged in the... This is crazy, guys. This is crazy. I plugged in the keyboard to the charger, but it doesn't work. Okay, we'll improvise. Cool. Okay. Okay, let's try. So let's try to read the list of the product as JSON. Okay, just let me know in the chat if you still hear me. That would be great. I'll really appreciate that. And let's run it in the meantime. How fast is it on the CPU? That's a very good question. I actually don't know. Yes, we can. That's great. Sorry, I mean, that's the first time. It's probably, I don't know, stream number 30. And that's the first time my keyboard decided to disconnect for some reason. I will not debug that right now. So I'm just using the keyboard on the MacBook. But ain't going to lie, it a little bit messed up my whole setup. So people from Indonesia that we have in the chat are reading the output, and are saying that there are some spelling mistakes. I'm curious if we would have those mistakes if the images would be like a higher quality. And I'm curious if Gemini would make the same mistakes. But like I said, I asked it to extract list of products as JSON, and looks like it works. We didn't provide the schema for the JSON, which is, you know, probably we probably should if we would like to have a consistent schema across different images. But even by default, looks like the schema is fairly consistent, yeah, because we have the items key, and then the list, and then the name price. Okay, and here's, you know, there are some inconsistencies, but I think that if we would like literally ask it to provide like a read the list of products, return as JSON, or maybe return. Of so now I'm trying to provide the information about like what I would like to extract. So read the products, return us list of JSON objects with name, price, and count keys. And we'll see how it goes. So like I said before, we didn't have like a consistent schema. We didn't really ask about it, so we didn't got it, but maybe now we'll get. So just in meantime, we see at least for the first one, we get the output in the format that we wanted. We also got some like additional keys that we didn't ask about, and those additional keys, they are not consistent. So sometimes we have total, sometimes we have cache change total, sometimes we don't have anything but only those objects. Here we only have probably one product, so that's why we have this. So no. So here I will try to ask it to literally return nothing else, just those. So no additional keys, like total, cache, and we'll see how it goes. So people are asking, is it heavy and can they use it real time? I will show you a demo towards the end of the stream where I built like a smart parking system. Anyway, maybe we'll run that cell. So we'll have that demo later in the stream. But the thing is, it doesn't feel that it slows you down. The speed of the model is actually fairly good. This is of course a GPU, so I'm not sure how it will run on a CPU. But if you run it on a small images, you can expect almost like a real-time performance, like multiple images per second, like 10 or 15. If you run it on a complex images, like right now we are running them on those cache receipts, it is a little bit harder, yeah, because it's more text to be generated. Yeah. So now it is almost what we wanted, but still not. Yeah, but definitely we can ask about the JSON output. I would suggest to use Pydantic to enforce JSON scheme output. Yeah, I mean, that's not the whole point of this stream, so I don't want to spend too much time on it because I want to show you next examples. But definitely, if you expect like a specific format of that JSON, then you probably need to specify it in a very precise way. Because what I did is I just asked it to return the JSON format, and it was returning the JSON format, but with like a different keys and so on. Now there is another one where I tried to make it work as I want to, and like it didn't really want it to do that. So we also have a data set of post stamps. I believe those are from US. And those are like very different from each other because they come from like different time periods. So they have all of them have dates. But what I would like to have is I would like to extract that date. First of all, extract the date. Second of all, like have it in a very specific format. Yeah. So, so I asked the model to extract the date from the image and return it in the specific format. What happened is that it extracts the date from those images, but pretty much keeps the date in the format that was on the original image. Yeah, so it's October 14th, 2022. But here, here is it the mistake? Not really, like it's exactly the date, but it reformatted it in the format that I wanted. Yeah, so here is April 2nd, 2010. Yeah, so that's the format that I wanted. But here, for example, it didn't follow my instructions. Here also, it didn't follow my instructions. It extracted the date in the format that was originally in timestamp. Yeah, so here was something that I noticed when I was building that demo, that it don't really want to follow those instructions about the format. And couldn't really get it to do that. Now that I think about, maybe we could like maybe let's explicitly ask it to reformat it, exclamation mark. We'll see. No, it doesn't really help, you see. Like it's even worse because that April that was working before doesn't work. So because something that I noticed is, yeah, this explicit ask for a specific date format, it doesn't really work. Next up, I have like a test with jersey numbers. And those of you who follow my demos online, you know, it's coming from our NBA or maybe basketball AI demo. So part of that demo that we built back then was, you know, tracking players, but also detecting jersey numbers and then reading the numbers from the jerseys. So those are like very small images. You can see individual pixels there because those are coming from like a full video of NBA game. And we detected them and we cropped them. And what we faced back then, I was using small VLM2, I believe. And the model, like we needed to fine tune the model because out of the box, it was not doing good enough job. I don't want to like, you know, give you false number, but small VLM was like wrong in like 50% of the cases. And after we fine tuned it, it was correct in like 80% of the cases. So it was still making quite a lot of mistakes, 20% of them, but way less often. And I'm actually not sure what number would that be. But here it's definitely 8. Here is definitely 2. Here is, I believe, 8. And it got detected as 18, 14, 40, 17, 5, 8. So we have like a 1 definite mistake and we have like 1 potential. I can see it to be 2. That's possible. So generally speaking, like it is fairly accurate, and that is a hard task to do. We need to fine tune small VLM to do it. And at least on that very small subset, it looks like it's as accurate out of the box as the small VLM was after the fine tuning, which would be pretty good result. And also the speed of that model is way faster than small VLM, because when I was doing the basketball AI, I wanted to probe and read the jersey numbers quite often. because because the model was 80% accurate, I didn't want it to just run it once and believe into that. So we had like a interval that we used to probe the number. Because small VLM was a lot faster, a lot larger and a slower model, it was slowing the whole pipeline down. And I think that this GLM OCR could be a solution to that problem. The next test that we have is the serial numbers from containers. So here the prompt is read only the container serial number. And what we see, and it's very interesting because some of those numbers are vertical, some of those numbers are horizontal, and it will be probably hard for you guys to see this. But here, for example, we have a vertical serial number MS CU 3829497. Yeah, and it was read correctly. But for example, here we have TSNU part that was not read correctly. Yeah, so I think it comes down to like being, it's pretty hard to know what is the serial number and what is not the serial number without any fine tuning. But it's doing like I would say good guesses. Yeah. So for example, here it took the whole number and printed that. But or for example, here it didn't print at this part, TS and U, and it didn't print at 0. Yeah. So for those cases like this, I would say you would still need to fine tune the model. I was trying different prompts. Because, okay, so maybe let's try read full container serial number. Yeah, maybe that will change something. We'll see. So now what happens, and that's why I had this only there, the model starts to read parts that I didn't want it to read. Yeah. So because on containers, you have more information than that's just the serial number. You have some dimensions, you have gross mass, there are some different things over there. And it starts to read those things as well. So I think that for tasks like this, we still would need to either have like a detector that would detect where is this container serial number, and then we would just run OCR on that specific section, or we would need to fine tune it to be just a lot more smart on like which part of the text it would read. Yeah, by the way, if you have any questions in the chat, let me know, because I'm just going through those examples. But I always appreciate any questions or suggestions or ideas, so just let me know. One of my favorite examples of like how awesome VLMs are sorry, I'm sick. Maybe you can hear that through my voice. But one of my favorite examples of showing how cool VLMs are at OCR, it is a serial number extraction from tires. So not really sure if any of you had a chance to kind of like build a system like this, but tires are notoriously hard to extract the serial number because, you know, they are round and there is like a lot of distraction and there is a lot of dirt on those. So all of that has, you know, a big impact on like how accurate you can be. And so it's always impressing me how those VLMs can do that. So for example, you have this continental tire over here, and there is like 61383, and then there's like 15722, I believe. But those serial numbers are so thin. Those numbers are so thin. On top of that, there is dirt, and you know, the light is also like making part of the tire a lot lighter. So it's doing really well on those tires. I believe I didn't find any mistakes. Just take a look at this image, like how hard it is to actually read something from here. And it's still doing pretty good job. So for example, tires, they went extremely well. And the last example that I want to show you, that will kind of like lead us towards the demo session, is license plates. So let's just download the data set and we'll just run the model. And here the prompt is like, read the license plate. Yeah, prediction on the dirty tire is insane. I agree. So, but I'm curious, like, is it something about those models? Are those tire serial numbers like literally part of those data sets so that it is trained to do things like this? Because take a look at this. This to me is a lot harder than the case with the containers. But for some reason, it's like hard for me to get the full serial number out of the box, but get the serial number from the tires like easy, even though that's an insanely hard task to get. Very interesting. Yeah, and the final one is plates. Yeah, so those are pretty interesting plates because, for example, in my country you cannot have like dots on the plate, but here you have. But we have like 1551, sorry, G 513.32. That is matching. That is matching. That is matching. So, like a very good accuracy of serial number extraction from the license plate. So yeah, so that's pretty good. Polska górą. Yeah, we have some Polish people in the chat. And for those Polish people in the chat, but not also for them, now we will have a demo. So I was like, okay, I like the license plate idea. Yeah, so let's build on that idea. So now I will show you the demo where we will, give me a second, maybe I will have like I would show you the raw video before we'll build the actual solution. Do I have that video? It's probably here. I will just show you through the link. So I have this video that's why it's for Polish people, because I captured it in Poland, near where I live. And I was like, okay, I would like to build like a very basic demo system for like automated parking management system. Yeah. So there are cars coming in. They come in on the left side of the screen, and there are cars coming out. They're coming out on the right side of the screen. Typically in systems like this, you would just have two cameras, one looking at one direction and another looking in a different direction. But just, you know, I didn't have enough time to capture videos this way, but that will be the typical setup. You see, we have people who are complaining about the license plate being wrongly detected. So maybe they should switch to GLM OCR. So this is the raw video. So now I was like, okay, how should we approach that? I actually built this demo some time ago, but I was building this demo with like OpenAI API and running the actual inference of the license plate using OpenAI API. But now, like, why would I do that? If I have like a model that is less than 1 billion parameters that I can run locally, and it takes sub-second time to run the inference. So I took the video, I took the left part of the video, so I have kind of like only the stream of cars incoming. And I decided to build a solution using RFD-ETR. So I fine-tune RFD-ETR on custom dataset I found on RoboFlow Universe. So let me show you this. Yeah, so I have this like license plate detection system with those plates. So I believe this is exactly the same data set that we used to evaluate. So I decided, okay, let's fine-tune RFD-ETR on this data set. And it got like a near perfect accuracy. MAP 50, 95%, yeah. So I fine-tune RFD-ETR on this data set. And here is, he reloaded that model. And here I'm just, running inference with that model. I'm selecting the frame because on the first frame there is no car. So I just pick one of the frames where I know that the car is, and I run the detection. So this is the detection part is, fairly simple. It's just RFD-ETR. And now here is the step where I'm running that detection on every frame on that video. It is like a minute-long video, so we have almost 2,000 frames to run, and you see it's running at 40 plus FPS. So the part to detect the license plates is very easy. Yeah, it's real time, easily real time. For a serial number problem, I guess they're standardizing an all bound beginning with 4 letters. What if you ask this in the prompt? Okay, so there is an idea that for that license plate problem that we just faced, we could just try to provide additional information in the prompt. I will do that. So give me a second. We'll finish this and we'll come back to that serial number of container problem, and we'll try to figure it out together. So here is the output video for tracking. Detection for now. Yeah, so the license plate is being picked up, and that's how it goes. Something that I didn't told you, I specifically asked the model to ignore any detections that are like smaller than 1% of the area of the whole frame, I believe, or 0.1%. So I didn't want to have too much blinking, and when the cars are too far away, they have those plates. Those plates are being detected, but the model is like not entirely sure whether or not they should be detected, so they are blinking. So I decided, okay, let's just ignore those smaller plates and just have a setup where we only care about those larger plates, those that are closer. And at the same time, if they are closer, they are way easier to read. So I don't care about those plates that are there because I know that I won't be able to detect them. To read them. Yeah. So I only care about those large enough. So here's the detection, and I remind you that detection was running at like 40 FPS. And now we run detection with tracking. So I'm using trackers. by the way, if you didn't give start the trackers project yet, I highly encourage you to do that. So I will, as a matter of fact, I will just paste you this link in the chat. So just leave the start there in the meantime if you can. And I'm using OC sort. So the setup is almost identical. The only thing is that on top of those detections, I will be using tracking. I'm using OC sort, one of the trackers that we recently added. And I'm using one of the arguments of OC sort, which is minimum consecutive frames. So the argument says we try to come up with the ID for the tracked object, but we'll only assign this ID when we'll have at least this amount of subsequent frames where that detection is being picked up. Yeah, and this gives us like a very stable tracks, because it's not like 1 or 2 frames was enough to get that ID. That object needed to be detected on like multiple frames before to get the ID. So here we are getting this ID assigned, but we see no number played yet, yeah, because we didn't run GLM OCR yet. We only run RFDETR plus OC sort. So there's that. And now when we see cars passing by, we see those IDs being assigned. And by the way, this moment when we see this gray box over here, this is the moment where we already have detections and the tracker is thinking about assigning this ID to that plate, but we don't do it yet. Now, why did I use tracking? So I use the tracking to prevent situation where we just spam GLM with queries for the same plate all the time. Yeah. So if I'm using tracking and I have stable track on a given plate, I know that I already run detection for that plate, or I know that I didn't run detection for that plate. Yeah. Like text recognition for that plate. Yeah. So that's why I'm using tracking, because almost doesn't cost me anything when it comes to time, because my average FPS with tracking is 43 and my average FPS without tracking is 43. So they are almost identical. Then it doesn't cost me anything to run the tracking, but on the other hand, it prevents me from doing expensive, like, it's a very small model, but expensive queries to GLM OCR. And now it's time to plug in the OCR model. Yeah. So I'm loading the model exactly as we did in the previous notebook. The only difference here is that, the pipeline is getting a little bit more complex because we need to have the tracker. I'm also preserving information about which tracker ID was already executed and which is still to be executed, so that I can do it only once for every tracker. I need to have that information somewhere. And also what I'm doing is I'm looping over detections for a given frame, and I'm cropping out part of the whole frame to run the GLM on it. Yeah, so I'm not running GLM on the whole image. I'm running GLM only on the crop that I know is the license plate. And I'm only running GLM on the crops that I know are the license plate that I didn't see yet. Yeah, so that's why I have this like registry to know whether or not I already executed for that plate or not. And here's the last video that I want to show you. This is with everything running start to finish. Yeah. So we see that we picked up the detection and we assigned the tracker ID. Now, if we wait long enough, we'll see that we extracted the plate number. And now the trigger for that extraction is, once again, the area of the detection. So I was like, okay, to prevent us running the OCR, for example, here, where the plate would be significantly harder for us to read, let me just introduce like a threshold saying that we will only run the OCR when we know the plate is large enough. That's pretty much what's happening here. Yeah, so we have a setup where I'm only running that once for a plate, and I'm only running it when the plate is large enough. If there are any other objects, many track IDs, that is still processed at 43 FPS. So the detection part will still run at 43 FPS. The tracker can be slower because the tracker have matching system, I believe Hungarian matching algorithm being used there, and it matches predictions. So tracker predicts when the object should be, and we have detections, and we need to match those predictions for every tracker with detections, and that is kind of like, can be expensive if you have a lot of objects. So if you have 10 objects, it will still be 43 FPS because that 10 to 10 matching is very easy. But if you have 300 objects and you have 300 tracks that are still active, then it's matching of 300 to 300 that can be slower. Yeah. So yeah, it depends how many objects you have. Can be slower, but at the same time, we won't see like a linear degradation like we see with some. For example, segment anything gets linearly slower. So if you have 2 detections, it will be 2 times slower than if you have 1 detection. That is definitely not the rate of degradation that we see here. Okay, so there's that, yeah. And when I run later part of the video, then we'll see that we pick this as well. So we get the ID, we get the number. That is correct. And now I know that it will make mistake right now. So pay attention. This one, I'm not sure why. Is it coming too fast, or what's the problem? But we got the plate, we give it the tracker ID, but it freaking comes up with this J. I believe this is why, because this kind of looks like J over here, but it's kind of annoying. I think that maybe if we would give more padding around the plate over here, maybe we would get it right, because it would have more context. I'm not sure. But it come up with that J, which was very freaking annoying. And the last one, this one works well. But actually, we pad boxes over here. Yeah, so I was unsure, maybe if we would pad it more. Let's pad it with more, like just for the sake of me, you know, being sane. Let's try to pad it more. So we got one mistake. And also take a look what's happening here. Like, because we only run GLM OCR once for every plate, the impact on the average speed of that processing pipeline is almost negligible. Yeah. So we can see that there are moments where the speed drops down to like 20 or 30, but that's because this is the moment where we want GLM on that specific plate. Yeah. And other than that, if you average it all out, it is still like 45 FPS. Yeah. So because we use this like tracking plus OCR setup, we don't have those problems where the speed is dropping significantly. So now I padded more. So the bounding box does not really represent the crop that we take. Now we padded a little bit more around this. So for this one, it is, let's say, okay. It inserted the space in between some characters, but it was okay. For the second one is okay. For the third one, you see, now the third one is okay. So the moment when we gave the model more context around this area, so we cropped probably this much, it then knew it is not the J. It is like a part of that plate, and but it's not the character. So you see, there are some tricks that we can apply to make the result more stable. So now, for example, with that padding where we padded not 10 pixels but 50 pixels, gave the model more context, it was getting things right. Okay. Before we wrap up the stream, what I would like to do is come back to this container example where we had an idea on maybe improving the results. So read only the container serial number in, and what is the format for that serial number? It's like character. So CCCC space. Whoops. Then we have number, yeah. Number, so 6 numbers. Then we have space. Okay, so number. 1, 2, 3. Then space, then another number. And then 4 numbers, I believe. Format when. C. So it is a more advanced prompt to maybe force the model to read the serial number of the container in the format that we would like to have. I'm not sure if it works, but I think it's like Eric suggested that in the chat, and maybe now it will give us more. But like we saw with the dates, I'm not sure if the model is this good when it comes to reading what we want. So for example, what do we have here? It read part of that correct. Now here, it read this part correct, but did not read this. Wait. It doesn't, it is not correct. Yeah, because here it is character, not a number. So it is like CCC, then 6 numbers, then 1 number, then number, character, number, I believe, yeah. Let's see. So I'm just trying to provide the model with more context. But yeah, I am not sure, to be honest with you guys, if it helps. Like we established with this, yeah, when we try to give the model like a requirement on the format of the output, and we are not talking about the JSON or table, but like a format of the text, date, serial number, it is not doing great, guys, for those cases. I would say this is like the only downside of this model is that us trying to force the format of the output, like we saw with the prices or as we saw with the dates, or now with the like a specific format of the serial number, it is not doing great. But I believe that if we would have a model that would just crop it out for us, then we would be able to boost this performance by a lot. And I'm not sure if we have model here. I'm not sure if I want to build it right now, but so we have some models, but you see, I don't think it would work because that annotation is probably incorrect. Because what we would like to have is like a single bounding box around all that and just say, read the text from it. And because those are two separate bounding boxes, it would get the text from here and it will get the text from here, but it wouldn't know how to like then put those two together. But I'm pretty sure that if we would have like a well-defined detector, then we would be able to extract those. Or we could just fine-tune the OCR model to do it for us. Either way would probably work. Okay, that's everything that I wanted to show you today. But I'm super happy to answer your questions. So if any of you have questions about the model or the demos that we did, anything that we did today, just drop some questions on the chat, and I can stay a little bit longer with you guys and try to answer your questions. And if not, if nobody will have any questions on the chat, then I'm happy to wrap it up for today. I'm still impressed with you guys that you stayed here for 71 minutes of me being sick and talking about GLM. So I really appreciate that. So yeah, like I said, I will wait a little bit because I know that there is a delay between me talking to you guys and me, you hearing me and asking questions in the chat. But if any of you have questions, I'm super happy to answer. Don't see any for now. So maybe nobody has questions. If nobody has questions, by the way, let me just ask you for one favor. If you could leave a star on our notebooks repo and leave a star on our trackers repo after this stream, I would greatly appreciate that. I need to, show my manager that there are people interested in those projects. So make sure to do that. Maybe we'll have more streams about tracking then and other models as well. So I'll do it. Have a rest. No questions. Thank you very much. I'm trying to get healthy for the past literally 3 weeks, and I'm constantly on and off, sick and feeling a little bit better. Sick and feeling a little bit better. The whole 3 or maybe even 4 weeks. It's pretty hard. This will definitely help my dad in reading his recipes. For sure. If I would be so happy to hear that you guys built something with the ideas that I gave you during the stream. Make sure to let me know on Twitter if you guys built something. Okay, I don't see any questions. I hope you liked the stream. If you did, like I said, leave the star on our repos, notebooks, and trackers and RFD ETR. And yeah, a different camera perspective than usually, because all of those shenanigans with cameras and keyboards. But I hope that you like the stream. And yeah, see you next time. I yeah, I'm very glad that you guys stayed here this long, 74 minutes. That was a pretty cool stream, I think. See you. Bye-bye.